This is How to Math with Dr. Ian Lundholm. In today's episode, absolute and conditional convergence. All right, we're in section 10.6, and here are the main topics for today. Today's actually going to go pretty quick. I want to remind you that page 821 is that great little summary of convergence tests of all of the things that we've been looking at in this chapter. So that is a good sheet to look at when you're trying to study all of them together. So the first thing for today, alternating series, talk about what those are, and then we will decipher between absolute and conditional convergence. Okay, so far, we've looked at series. Some of them have ended up being divergent, some have been convergent. Today, we're going to be looking at a subsection of series where we look at a difference between absolutely convergent and conditionally convergent series. And these things only happen when you're working with alternating series. Alternating series, like this one, or this one, are named alternating series because their signs alternate positive and negative for each next term. That first series that we have here looks pretty geometric to me, with a constant ratio of negative 1/3. This next one looks pretty linear to me, and the terms in that continue to grow unbounded, so I don't have much hope for that one converging. And then this last one looks like the harmonic series, except the signs are alternating, and therefore we give it the very creative name alternating harmonic series. So let's take a look at each of these real quick. That first one with the geometric series, the common ratio was negative 1/3, and it's actually fine just to put that into our normal geometric series formula. That common ratio, it does have an absolute value that is in between 0 and 1. And it works out that, the entire sum is negative 9/4. So that's cool. Yeah. Then the second example here, where the numbers were just increasing linearly from 1 to 2 to 3 to 4 to 5, that one definitely diverges because those numbers are growing without bound. So no surprise there. And then we're going to look at the alternating series test, and see that the alternating harmonic series actually fits this alternating series test, and therefore will be convergent, or at least conditionally convergent. Here's the alternating series test. Our ANs here are all positive terms for this, this notation. Two big things. We want the sequence of positive terms to be monotonically decreasing. That's part one. And we also want the terms to approach 0 as n goes on. So for this first part, we are looking at the series, just looking at the series terms, without the negative 1 clouding things up. But what this test does is it tells us that the alternating series converges, and that does have the powers of negative 1 in there to give the alternating signs. And so yes, in short, if the terms of an alternating series decrease monotonically to 0 in absolute value, then it converges. We can quickly look at why that occurs. I guess first it's important to make a note that remember that we're really concerned with the tail end behavior of series. And so if this is true for all n past some given n, the result's still true. We're only concerned about the tail end behavior. The proof for this relies on looking at the sequence of partial sums, but specifically the partial sums with an even index. And so we're always taking these differences between terms that are next to each other, where one of them is positive and the other one is negative. First, since we have this condition, condition number 1, that an plus 1 is always less than or equal to an, all of these differences are going to be positive. And that's why you see that, for example, here, S4 is greater than or equal to S2, and S6 is greater than or equal to S4. All of those differences are, I guess, non-negative, either positive or 0. And so what's important to note there is that we have a monotonically increasing sequence of partial sums. Monotonically increasing sequence partial sums. Cool. And that's specifically for the even partial sums. We'll talk about the odd ones soon. But on the flip side, we also know that starting off with, a positive number a1, that this partial sum will be less than the first term a1 if you're starting with, a positive number for a1. And you could cut off the first, however many terms that you want from the beginning to make sure that you're starting on a positive number. Because again, we're only concerned with the tail end behavior. So a1 here is some positive number at the beginning, and then we're subtracting off the rest. And so a1 acts as, an upper bound on that sequence of partial sums that is monotonically increasing. And what do we know about bounded sequences that are monotonically increasing? They converge. So yes, the bounded monotonic sequence theorem says that those even index partial sums converge. For the odd index partial sums, know that those are very, 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 very similar to the even index sums, except for the fact that they are one term different. So there's one term different. And since those terms go to 0, the odd index partial sums converge to the same number as the even index partial sums. And we get that, we've got everything approaches S as n approaches infinity, and the entire series converges. Cool. And these examples are a little bit weird. There's not really a first slide that gives you an overview of everything that we're going to look at. But here's example 1, and the first series that we'd like to look at is the alternating harmonic series. And this series does check both of the boxes. We would start off with a number like 1, and then subtract off a half, and then add a third, and subtract a fourth, and so on. If we look at are the absolute values of the terms, here, let's see. yeah, decreasing over time, yes, we do check that box. Because 1 is greater than 1/2, which is greater than 1/3, which is greater than 1/4. That box is totally checked. So we are monotonically decreasing in terms of the sequence terms. And those sequence terms do approach 0 as n goes to infinity. Yeah, sorry, equals 0. This is limit. Good grief. And yes, we definitely check that box as well because, by the end of this, we'd have 1 over something that looks like infinity. So yes, the alternating series checks the 2 boxes that we needed to check for the alternating series test. Moving on. Here we have another alternating series, a linear factor on top and a quadratic factor on bottom. If we were in a different section, I might start attacking this using I don't know, the limit comparison test, something like that, to where we could compare this to a series that is similar but more familiar. Since we've got n to the first power on top and n to the second power on bottom, this thing will behave a lot like the harmonic series overall. But we do have the complicating factor that there is an alternating -1 over here. So I bet this thing's going to behave a lot like the alternating harmonic series. Let's go ahead and take a look here at how to analyze this too. The first part is we want to see if this thing is, all of the sequence terms are decreasing monotonically, at least at the tail end. So at the beginning, if you were to throw in n equals 1, n equals 2, n equals 3, this thing wouldn't look like it's monotonically decreasing. But after you get past 4, this derivative, and now it's written in terms of x instead of n, but this derivative is not positive, and so it is a decreasing function as, x would go on here. And so we used some calculus there. We used a derivative to show that this thing would be decreasing monotonically after, x is greater than or equal to 4. So we've got the monotonically decreasing part for the sequence term, or the series terms. And then we would need to show that those terms do approach 0 as n goes on. And indeed they do. It's a limit. Just dividing by n squared on top and bottom. No big deal there. Cool. And yes, this only satisfies the conditions for n greater than or equal to 4. And, that 4 is our big N in this case. But yeah, we're good. We're only concerned about the tail end behavior. The proof that we looked at for the alternating series test is going to point our way forward for getting estimates on the remainder for an alternating series and how quickly the alternating series converges towards its actual limiting value, its actual sum. And the hint that was in our proof is that we look at a bunch of these differences between successive terms. For instance, a1 minus a2 or a3 minus a4. Those differences are going to tend to be really small, and we're going to be able to use them to put bounds on our partial sums. So, yeah, in general, the S sub 2n minus 1th partial sum is very close to the S sub 2n plus 1 partial sum. And the difference is just this difference between two successive terms. And that difference tends to be really small. So, yeah, that gives us a remainder estimate that the remainder will be, so yeah, like the distance away of how far we are off at any given partial sum, this remainder is less than or equal to the n plus 1th term. It's really just that easy. So, for instance here, we have an alternating series where we've got a factorial on the bottom. And we could take a look to see how far out would we have to go to figure out the first 3 digits of that decimal number for sure. And really, if you just go out for the first few terms, we're fine. Here is S sub 6. This would be, all of those added together would be the 6th partial sum. And a 7 is just this one. And here the calculation is done that S6 is about this decimal, and a 7 is this. And so just by going out, for these 6 to 7 terms, we know that we are very, very, very close to the actual value of this infinite series. We're at least correct to the first 3 decimal places. And here we get to talk about absolute and conditional convergence. So, we've mentioned the alternating harmonic series already. But notice that if you take the absolute value of all those terms, it becomes the harmonic series, which does not converge. And so the alternating harmonic series is what we call a conditionally convergent series, because its absolute value version does not converge, but the alternating version does converge. So here, I'll do this, but I'm going to make it into a chart real quick so that it's easier to read. But the chart was in my head when I looked at the last slide. Anyways, I might be able to get it here after I read this. We say that this series converges absolutely, or is absolutely convergent, if this corresponding absolute value series converges, but it's conditionally convergent when this one doesn't converge, the absolute value version. So yeah, absolutely convergent. Okay, here. This is what I wanted to do. This is absolutely, and this one's conditionally. Whoop, 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 whoop. For absolutely, both converge. Converge. This one converge, oh geez, and diverge for this part. And so an example of this one would be, I don't know, the alternating harmonic series. And an example of this one would be, I don't know, like something like what we saw earlier where we're alternating, but it's a geometric series instead. That would converge either way, even if there was no alternating part to it. Okay, so that's absolute and conditional convergence. And certainly, absolute convergence implies conditional convergence. So, yeah, if you get this thing to converge, where all of the terms in the series are positive, that's much harder to make converge than this one, where you could have negative terms and there could be some cancellation. So that one's pretty straightforward. I don't even want to do that. Here again is that series hierarchy where we have absolutely and conditionally convergent series. Here are a few examples before we finish. Here we've got this series. And again, we've seen series like this before. This one would be absolutely convergent. We could prove that that thing converges using something like a direct comparison test where, yes, the series is bounded above by 1 over n squared, a convergent p series. And so, yes, it's absolutely convergent. Even, I'm not necessarily in love with this example because while sine of n would change sine, I'm not sure that it would change sine every single time that you changed n. Does sine behave that way with integers? I don't know if that's a proper alternating series, but it certainly is absolutely convergent. So yeah, I wouldn't say that this is a proper absolute. It's not a proper alternating series, but it is an example of absolute convergence. That's not a big deal. Here we go. Looking at the entire class of P series, we converge absolutely for the P series that we've looked at so far, where, we have the condition that P is greater than 1. But we get conditional convergence, and this is the new part. We do converge in an alternating series even when P is between 0 and 1. Because there is cancellation that happens. So that's cool. And again, to see that this thing would converge conditionally, we apply the two-prong test. Would the terms in the series monotonically decrease as n goes on? The answer is yes. And would would the terms approach 0 as n goes on? And the answer is also yes. So this thing does converge as an alternating series, but wouldn't converge as just a normal P series for those values. So that part is conditionally convergent. Here we go. We have, this thing where we've got a lot of n powers. Taking the root test definitely makes sense here because we've got n's in the powers. And yes, even absolutely, this thing would converge. Even ignoring the alternating part, this thing converges. So we've got absolute convergence there. Here we have an alternating series. It looks like a mashup of a geometric series, but also you've got this n cubed thing on top. the geometric part's going to win out. So yeah, we could apply the ratio test and see that yes, the ratio of successive terms approaches 1/3. And so this is also absolutely convergent. Doesn't even matter that we have, a -3 there. So there's a little quirk here about series and the ordering of the terms. Absolutely convergent series have the property that any rearrangement or reordering of the terms of the series produces the same sum. So just reordering the terms doesn't change the value of the entire infinite series. But weird things happen when you have conditionally convergent series. Riemann showed that the terms of a conditionally convergent series can be rearranged so that the sum of the series is any pre-selected real number. And rather than sitting here listening to me ramble on more, I have selected a few videos from YouTube that introduce you to rearranging terms in the alternating harmonic series and how you can create different values. It's actually pretty cool. And I tried to pick some, entertaining videos. So give one or more of those a look. And I think that's where I will call it a day for this lesson. Do remember that on page 821, this summary of convergence tests exists. We've already talked about all of these. We've talked about p-series and direct comparison. We've talked about limit comparison and ratio. We've talked about root. Today, we've talked about the alternating series. And is that really the last? I think that's the last actual series test. If I had to go, now I'm on the spot. Where are we going next? It was in a PowerPoint. No, it was on OneNote. Hold up. Almost ready. There we go. Okay, so this was section 10.6. On section 10.7, 10.8, and 10.9, these are going to take a little bit of a turn, and instead of just looking at, infinite series of numbers, we're going to be working with things called power series or Taylor series, where we introduce a variable into each one of those terms, like x, and talk about for what values of x would those infinite series converge and stuff. We'll talk about radiance of convergence. And so the next 3 chapters won't be so much about different convergence or divergence tests. It'll be more bringing it back to functions like we're normally used to talking about. And Taylor series are a really cool place to kind of end the class overall, because it really allows us to explore calculus on a deeper level. We're able to, estimate, we're able to create polynomials that approach, like infinite series that, each of the terms looks like a monomial. That approach more familiar functions. So we're going to find a Taylor series for, most of the familiar functions that we've looked at so far. It's going to be fun. So, okay, I'm going to end this video and I'll see you in the next one. Bye.